Okay, so let's start out with the early internet. What did that look like? So what we're talking about here is the 1960s, the early 1960s. I would like to say, and yes, I can actually say that was before I was born. Whew, good. But so the early internet, some terms you may have heard of before, DARPA or ARPA. So DARPA stood for the Defense Advanced Research Projects Agency, okay? And the early internet started out as a project from, I'm not sure if I'm pronouncing it correctly, if it's just, if people say DARPA or DARPA, never actually really looked that up, but it started out as a research project from them, and they created something called the ARPANET, the ARPANET. And originally, way back in the day, the ARPANET was very simple. It simply consisted of two hosts, which were mainframes. So this is even before laptops or PCs were generated. You had these two monstrous computers that were talking to each other. And that was the early form of networking, having one mainframe be able to connect and get the resources of another mainframe. It was a point-to-point connection using circuit switching lines, actually using the phone lines. The mainframes were located at different universities, different colleges. I think they were in the same state originally. I think they were both in California originally. But they used basically the telephone lines to get to each other and transfer their data. Wait, went a little fast there. So keep in mind, back in these early days here, there was no such thing as a LAN, as a local area network. And this is important to conceptualize because I don't know if you're like me or not, but when I try to visually picture in my mind data going across a network, the image that comes to my head is, number one, I imagine data coming in to my laptop, so inbound or ingress data. And I envision that as a series of electrical pulses, right? Zzz, 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 electrical pulses coming in, and these electrical pulses are being interpreted as ones and zeros, right? So my NIC card is seeing this electricity bouncing around on the cable, and it's interpreting that as a series of just thousands of ones and zeros coming in really, really quickly. And when I think in terms of sort of the OSI model and the stack and all that stuff, the first thing that comes to my mind is, okay, those electrical pulses, that's my physical layer, that's layer one of the OSI model, the electricity coming into the NIC card. And then I start going up the OSI model. This is the way I envision. I say, okay, well, the next one is the data link layer, layer two. And at the data link layer, my NIC card says, okay, let's see here. What rules am I following? What protocol am I following? Oh, I'm doing Ethernet. So according to the rules of Ethernet, the first few pulses of electricity are the preamble in the Ethernet frame. The next few pulses of electricity are the destination MAC, followed by the source MAC, and then eventually layer two says, I'm done. I've looked at, a few hundred bits. I've been able to interpret that as an Ethernet frame. Within those few hundred bits, it told me that the next section is going to be IP. And so now we go up to the networking layer. So when I visualize this, I start at layer one, I go to layer two, and then layer three and on up. And why I'm bringing that up right here is because originally, when the original ARPANET was designed, there really wasn't a layer two. I mean, there was a layer one, right? It was a circuit switch line using telephone lines for one mainframe to call another mainframe, but there was no such thing as Ethernet originally back in these days, back in the early 1960s. So there was no such thing as MAC addresses. A lot of times people assume that historically layer two came out first, MAC addresses, and then IP came out after that. But it's actually just the opposite. TCP/IP came out before local area networks came out, before Ethernet. So as it says here, all communications originally were point-to-point. And initially it was like circuit switching, which is another way of saying the phone lines. And then as more and more networks started coming up, they were still point-to-point, one device talking to another device, but they started using other types of media at the physical layer, like satellite uplinks, like direct cable connections. When I don't mean like cable modem, I mean like a physical hardwired cable from one mainframe in one building to another mainframe in another building. That's what I'm talking about there. So as these point-to-point networks were being developed, as it says, there was a need to develop a protocol so that hosts on these disparate networks could communicate with each other. So the idea was, okay, I've just developed a very primitive network where my mainframe can talk to another mainframe. Now, what if I expand that to where my mainframe now has the ability to talk to 6 other mainframes? Still direct connections. What if I expand that a little bit further? What if I say, I want my mainframe to talk to, Sally's mainframe and then jump through Sally's mainframe to Bob's mainframe on the other side. Now, it's not point to point, it's me talking to somebody else and then going through them to somebody else. And they start saying, okay, well, we need some sort of address to do that. So when I connect to Sally, I need to have some way of telling her, hey, I don't really want to talk to you. I don't really need your data. I just need you to take what I'm sending you and pass it on to Bob behind you. And so this is where the whole idea of TCP/IP originally became invented. They said, okay, well, we need some sort of address so that when I'm sending my data to Sally, she knows it's not for her, it's for the person behind her, so she can establish a connection. And we also need to figure out some ways to make that data reliable. Like, how do I know if I send something to Bob way out there, how do I know if it got there? How long should I wait before I determine that, oh, doesn't look like it got there, what should I do about that? So they actually developed TCP right along the same time as IP. So TCP was developed to answer questions of how do I make this very unreliable, very primitive connection reliable for me? And what do I do when stuff is lost? And then of course they put IP along with that so we could have addressing. Now, just to give you some interesting terminology, back in the original ARPANET, these 2 or 3 colleges or universities that had mainframes talking to each other, that they actually developed a whole unique box, a whole unique system that the mainframe would connect to. And then these boxes, these black boxes, is actually what formed the network. These black boxes would use the circuit switching lines to talk to each other. And they were called, has anybody studied the history of the internet? Does anybody know what those original, I would say, routers, what was the name of the very first routers that were developed that these mainframes connected to talk each other? Does anybody know? This actually has kind of a funny sounding acronym. They were called IMPs, or Internet Messaging Processors. They were huge. They were like the size of a refrigerator. And of course, the mainframe was like the size of your whole house. But the mainframe would connect to this big refrigerator-sized box called an IMP. And it was actually the IMP that needed to be addressed. The IMP needed to have an address so it could talk to, the IMP in Stanford could talk to the IMP in Berkeley, or the IMP in Stanford could talk to the IMP in Los Angeles. And so that's where they originally came up with the idea of layer 3 addressing. Okay, so the main point I want you to take away from here is that, number 1, the very, very first networks were point-to-point only. Because number 2, there was no concept of local area networks. There was no concept of something called a broadcast domain where a whole bunch of devices could see each other on the same wire. That had not been created yet. So this is what networks look like. Back in the early days, you had these internet messaging processors connecting to always up circuit, permanent circuits. And the original layer 3 protocol that they used to address these things actually wasn't even IP. They came up with a precursor to that, which was called the Network Control Protocol, NCP. And NCP didn't even really, the only kind of addressing it used was like for port numbers. Like whatever protocols were running on that mainframe, each protocol had sort of its own unique port number, and that's how they addressed things. And then of course we had dial-up circuits where people would use modems to connect to each other, or satellite networks. So these were the early days. Then people said, and this is what I described earlier, say, well, what if I, in the future, need to jump through something? What if I need to connect, as we can see here, this mainframe on the far left wants to connect all the way to the mainframe in the bottom. So we've got to jump through a couple things to do that. So, it was the vision of these early internet pioneers that if somehow people could connect these disparate networks together, a satellite network connected to a modem network, connected to a dial network. If they could somehow connect all these things together, you would now have networks connected by a series of hops. And so there was going to be a need for some kind of networking addressing scheme, flow control, error correction and detection and all that stuff, and that is where TCP/IP was born, with the need to solve the problems introduced by what you see right here. So the original designers of TCP/IP said, okay, well, one of the things we're going to need is each hop in the network is going to need an address. So when we send data, that hop knows, is that data for you or for someone behind you? And so the original designers of IP said, okay, well, let's see here. You know, everything is viewed by computers as binary. It's just ones and zeros, just a string of binary. So they said, well, in however many meetings they had, they decided that address is going to be 32 bits long. They said that a unique network address is going to be 32 bits long. And they said, okay, well, you know, remember, this is like the late 1960s now, like 1969, 1970. And at this point in time, there's literally a handful of these networks. And so they said, well, let's see here, a 32-bit address, I don't really see how there's ever going to need to be any more than a couple of hundred networks. I mean, this is all experimental. We're just seeing if this works. So of this 32-bit address, we'll just say that the first 25% of it, the first 8 bits, will represent the network. And then the remaining bits will represent that unique IMP or mainframe on the network. So keep in mind, the original IP address was 32 bits long, just like it is today, but key difference was it was understood that of that 32-bit address, only the first 8 bits at the front end represented the network address. And if you think in terms of binary, you realize that with 8 bits to play with, you're pretty limited in how many networks you have. As a matter of fact, you only have 254 networks available. Now with 8 bits, technically, if you think of every possible combination of binary you can come up with, from 0000 up to 1111 and everything in between, technically that gives you 256 combinations of numbers, of bits you can come up with 8 bits to play with. But the early designers of IP said, well, 2 of those combinations are not going to be usable as an address. The combination where the network is all zeros, so the first 8 bits, if those are all zeros, that represents like a default route, a route to anywhere. And then the other combination is if all of those bits are ones, that's considered a broadcast. It's like sending something to anybody. So those 2 numbers out of 256 you could not use, that left 254. And back in like 1969, 1970, they were thinking, oh, we're never going to use 254 networks. I mean, this is experimental. This is for fun. Of course, we know that didn't turn out to be the case. Now, what's kind of interesting is it was actually very forward thinking of these people to come up with a networking address where you had a network address and then a bunch of host bits. Because if you think about it, there were no LANs back then. There were no broadcast domains. It was just point to point. They could have come up with a scheme where they said, okay, every device is just going to have a 32-bit number. We're not going to divide this between network and host. You're going to have a unique name. I'm going to have a unique name, or we're just all going to know each other's unique names. But they didn't do that. They took this 32-bit number and they divided it. 8 bits for the network, 24 bits on the end for host. And because they did that, it was setting the stage for a few years later when LANs and Ethernet would come out and those host bits would take on a lot more relevance. So we can see here, in this particular case, we've got 4 unique networks. So if we only have 8 bits to play with, they would say something like, okay, network number 1, you can see there, it's going to be 7 zeros followed by a 1. Network number 2, it's going to be 6 zeros followed by a 1 0. So as long as those 8-bit patterns are unique from each other, they're different, they can be recognized as being different networks. All right, now here we go into the 1970s. And so in the late 1970s, now Ethernet and token ring came on the scene. Some of you guys might be saying, token ring, what's that? That's not part of the CCNA. You're right. Token ring died out many, many years ago. But back in this day, they were competing layer 2 protocols, data link layer protocols. And both Ethernet and token ring were founded on the same idea, that you could have a bunch of devices, still probably mainframes or big servers, but a bunch of devices all connected to some common network media and able to see each other, able to talk to each other. So for example, Ethernet, the original Ethernet was a big, thick, sort of coaxial cable, very similar to the cable that goes into your cable TV set. It was big, it was yellow, it wasn't really bendable, and the idea was you could have several mainframes all clamped into that same cable, and if they were running Ethernet, now they could see each other on that cable. That if any mainframe started transmitting voltage, started transmitting electricity on that cable, you had more than one device on that cable that could see it. And so this is the whole idea of a broadcast domain, right? A broadcast domain is a collection of devices connecting to a common network media. Let's just say it's a cable to make it simple. And in that broadcast domain, if one of those devices starts using that network media, starts transmitting electricity on it, voltage on it, all the other devices see that. They're privy to that. So that was different, right? Back in the early internet, it was just 2 devices connected to a cable and that was it. Now, with Ethernet, you've got the concept of 3 or 4 or 5 devices could all be connected to that same cable and they could all see each other. So now we had a requirement that did not exist previously. You know, previously with just 2 devices on a cable, when device A started fluctuating the electricity, there's only one place it could go, device B. Device B knew, okay, if I see some electricity coming in, some ones and zeros, it's gotta be for me because there's only me and device A on the cable. There's nobody else it could be for. So there was really no need for any kind of addressing at layer 2. Because it was point to point. Well, now with a broadcast domain, with Ethernet, we do have the requirement for an address. Because now we could potentially have 30 devices all seeing that same electrical energy, all being privy to these ones and zeros going across the cable, and now they need to know, is that for me? Or can I safely ignore it? So that's why with Ethernet, they said, okay, we need to build in an address called a MAC address, a layer 2 address into Ethernet, so that when I put stuff on the wire, I can address it to a unique individual. And so when I see stuff coming on the wire, I know if it's for me or if it's not for me. Now also keep in mind that the original developers of Ethernet and token ring, they said, well, you know, Ethernet and token ring, there's protocols out there right now that it could carry, like Ethernet might be carrying IP behind it. But maybe in the future, someone will develop other types of protocols. We don't want to limit, as a developer of Ethernet, let's say I'm the designer of Ethernet, I don't want to limit or restrict myself to where my Ethernet protocol is only ever going to be able to carry IP packets. I want to design it so it's fluid, so it's scalable, so that if anybody develops another protocol 5, 10, 15 years from now, my Ethernet protocol, which was developed way back in 1972, can carry that new thing. So this is why Ethernet needed its own unique address. You know, a lot of times when we think of Ethernet, logically in our minds we think, oh, Ethernet carries IP. Ethernet carries IP. Well, that's true, but Ethernet can carry hundreds of different protocols, not just IP. So the designers of Ethernet were to assume that a frame might carry non-IP protocols, so they put their own address into an Ethernet frame.